Hello and welcome. My name is Armin Katowic. I work here at EQT in the Motherbrain team. I'm one of the machine learning engineers here, and I'm also on the board of Stockholm AI. And one of the things we do is we do these awesome events where we have very interesting presentations by very interesting speakers and fantastic audience. So Stockholm AI, just a quick background, if you haven't been to our events before, don't know what Stockholm AI is about. It's a non-for-profit that essentially runs a bunch of meetups, along with a few other things like mentorships, etc. And the whole purpose of Stockholm AI is to try to spread the knowledge in the field of machine learning, data science, artificial intelligence, data engineering, etc. In Stockholm and the Nordics, and make everyone more informed and make the Nordics the capital of AI. Right. So if you're not a member, I'll actually get to that in a second. What I also like to do is I'll like to say thanks to our sponsors. So Talavox is our big sponsor that actually gives us some money that allows us to, for example, buy food and run these events for free. So that's very, very nice of them, and we thank them very much. We also have what we call sort of partnerships or venue partners, like EQT, for example, and EQT has been very kind to let us borrow these beautiful office on several occasions. We'll try to keep doing that. So we'll have another event coming up here in a few weeks' time, early November. Right. So, but if you are not a member of Stockholm AI, it costs you nothing. It's completely free. So just scan the QR code or go to our website, stockholm.ai, and just become a member, basically. So you'll get automatic invitations to these events before anyone else does. You'll get access to our Slack channel where we discuss a lot of interesting topics, sometimes very heated discussions, which is always a good thing. So yes, please join. And I'm not sure if I have anything else here on these slides, but so today's topic is on knowledge graphs, and we have 3 big presentations. And we're going to go from research to practical, essentially. So knowledge graphs, we have worked with here at EQT, and actually all the speakers are either current or previous EQT Motherbrain members. So we know quite a bit about knowledge graphs. It's like one of these things where you probably see it a lot online, popping up, in different applications. These days, it's often in the context of some sort of retrieval augmented generation or RAGs. So I think it's kind of like a bit of an enigma. So we'll try to unpack that today with all the presentations, so you get a better understanding of what they are, what they can do, what they can't do, where the limitations are, and where they can actually give you some strengths as well. So we'll have 3 presentations. The first one will be by Lele, who is the master researcher currently at King. And he's going to talk about CompanyKG, which was a paper that we co-authored here. And there's a few others of us here in this room that have also managed to somehow get our names on that paper, which was presented at KDD conference in Barcelona as well, which is quite impressive. So he'll talk about that. And then we will move on to, I believe it'll be Valentin and Hans. Valentin over there, who was also ex-Motherbrain, and Hans from Nobel Prize Outreach, where they did some very interesting work, which I believe Hans can and Valentin can give more details on this, but essentially it's about the new upcoming exhibition and how the laureates and how the different topics are connected. And a graph kind of seems like a natural choice here. And then we'll wrap it up with Drew, my teammate, Drew, who is going to talk about more practical applications of knowledge graphs and how they can be applied and if they're successful or not so successful. But either way, it's amazing learnings and really good takeaways that you should definitely bring back with you. So let's give a round of applause to Lele. So before you start speaking, I will just go and unmute you.
Hello? Good. Thank you. I realize this is not the right screen, perhaps.
That's interesting.
Now it shows. So
No, it shows. Okay.
yeah, perhaps now it's correct.
It's like a delay.
Yeah, somehow it delays for a minute. Yeah, we have done that action like 20 seconds ago. All right, but I tried to switch the slides a bit earlier than usual. That's fine. Risk management. Okay, great to be able to present this work. As Arming introduced, this is one of the applied research kind of work that I did when I was working for the Motherbrain team, exactly here in this office. And recently, I switched my occupation to work for King, a part of Microsoft, to lead the research there. But this research is not exactly the kind of research you usually hear about, because it is super applied, as you can tell from the the title of this research. Actually, I've now just switched it to the second page, but somehow it shows this. It's,
Let's try sharing, and I'll try it again.
yeah, perhaps that's the way to go. Yeah, so this project, a bit of the background, in private equity business, many times we need to look into companies because of different reasons. Most of the time, it's because of some interests to the company, because of some expected investment activities. So in that case, you actually want to know, want to do a bit of analytics around the companies, trying to quantify the similarity between the company in your scope versus the ones that you're also interested in, or simply because if you want to, for example, look for competitors for the company, or if you want to see what are the potential merger and acquisition target for the company, for example. So in those cases, I think you always need some insights of similarity between the companies. When we are talking about similarities, it's not only about the overall measuring, like you can imagine a similarity score that you get from for a pair of companies, but many times you need to understand how they are similar and why that is the case. I'm not sure why this is not working. Is it because of its PDF?
Maybe it's the recording.
Is it the recording?
Or, yeah, it's some connectivity issues, basically.
Okay, let's try it again. It seems better. At least I see you're scrolling. Or no? Okay. Let's try to manage this. I'm a bit hesitant to scroll upwards now. Let's start from here because I think this is fundamental enough. I said we want to model company relations. I'm not even doing anything. And this is not, my God. Yeah, this is the action that I just did. Yeah, some examples, basically. I just want to show you some examples that I talked about: market mapping, competitor analysis. I'm basically trying to make sense of the example, some use cases that we are going to use this work for, by the way. And here the illustration of the screenshots here basically tells you how does it look like when you work with, in this case, it's a merger acquisition work. Usually what investment professionals do is that they collect, let's say, I'm just giving you some kind of random number here, maybe 100 companies that they know of, that they hear of, and then based on the merger and acquisition target, they try to rank those companies. So you ended up with those ranked company list. The top ones represent the most interesting one to be merged, or you pick up the phone and call the CEOs of that company, perhaps. I'm not sure how exactly that is done, but don't look too much into this screenshot, because this is just for making sense of the example. Okay. And because I try to avoid doing too much scrolling, there are other use cases, as I mentioned. Competitor analysis, basically you come up with, you want to search for a lot of direct competitors for the company on a specific market, right? Market mapping basically is a process that you try to identify as many companies as possible for a particular sector. Let's say the real estate platform companies in Nordic countries. Then you just collect as many of those companies as possible to your list to track the status of this whole sector. Okay. And then we can see that all of those use cases, at least the 3 use cases that I mentioned, sorry about the clunkiness of introducing these 3 use cases because of the dragging presentation, but all of those 3 use cases, they all need comprehensive measure of company similarity, as you can imagine. This is the fundamental of the success of those activities. So we were thinking about how to facilitate this kind of investment activities. We need to start from something that we have, something that's simple enough. So we thought about, okay, in our data set, in our database, we have descriptions of companies, right? Usually those descriptions is coming from different sources. It could come from web scraping. It could come from third-party data sources. So we collect those company descriptions. And then here is an example. We use ID 1 and 5 to identify 2 companies. Don't ask me why 1 and 5. It's just 2 numbers. And then for company 1, we have a description saying company 1 is a service provider of blah, 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 blah. And company 5 is a manufacturer of something, right? So in order to leverage those descriptions, we cannot just store the original texts. At that time, by the way, this project was initiated about probably more than 2 years ago. At that time, we were using some language models, pre-trained big language models, to embed those company descriptions into vectors. And in here, we utilized 4 different kind of pre-trained large language model. One of which is ADA2. ADA2 was the embedding model for, is it GPT 3.5, I think, if I'm not mistaken. Among those 4 models, PAUSE, if you look at the bottom one here, PAUSE, is a model that's actually devised by ourselves. And that work got accepted and published in EMNLP Research Conference 2022. After doing that, for each company, we have four different vectors that represents its textual descriptions. But this is actually far from enough. Because of course, by measuring the similarity of text, you can tell a bit how similar they are. But you are also lacking a lot of relations that you can actually capture from different data sources. Here, I took an example from how employees flow between two companies, how they change their jobs and flow between company 1 to 5 or 5 to 1. And by the way, when we are modeling this relation, we don't treat it as directional. So we are just calculating how many employees is actually exchanging between these two companies. And we normalize this number as the weights of this link between 1 and 5. So if you treat it as a graph, as a really small graph with two nodes, then this graph represents the relations of company 1 and 5 with one type of relation symbolizing how employees is being like exchanged or flowing between the two companies. And this represents a kind of similarity. You can argue if it's really a similarity, but you know, a lot of weak signals can add up to a strong signal, right? So this is just like one example, and the other examples could include, for example, event attendance, like Stockholm AI meetup, right? If you represent a company and we somehow get the information source, then we can count how many times have you been attending the same event in the past, and we count that number and normalize that as the strength of this relationship. Other examples include product user. So if you, as a company, produce some product and this product is used by a common user, then this is also a kind of relation that we build into this graph. Final example, co-appearance in news. So if you read newspapers or online news, you could find sometimes in the same piece of news, two company names shows up in the same news. So we capture that as a relation too in a graph. And there are more, right? It depends on what kind of data source you have. You can actually model many of those relations that can imply similarity between the two companies. And we define, now it shows up, and we define 15 relations of between those two companies. As I already mentioned, when we are building those relations, we are not only caring about 0 and 1, right? Exist versus non-exist. We also calculate some kind of weights of this type of relation, symbolized by the integers attached to those links, and the boldness of those links represent the strength of this relation between the two companies. Of course, this is just a visualization, but if as I mentioned, we have 15 different relations, and for each relation, we have those integers counting, for example, how many employees has been flowing between the two companies, how many times they attend the same conference in the past. So we put them together into the same vector. So for each edge between the company, by the way, between each pair of company, there is only one link or edge. And for each edge, we attach with this 15-dimensional weight vector. So this graph is actually a weighted graph. All right, so we have that. We have those relations built up with 15 different kind of relations, weighted. It's great. Now, this is sort of a bit of synthesizing of everything that I have been talking about. For each node, we have 4 vectors, which are the node feature. For each link between them, in this case, it's symbolized by E15. It has a 15-dimensional vector symbolizing the weights of those relations. And this is the smallest unit of the graph that we built. If we zoom out just a bit, you will see something like that, right? We have a lot more companies in our graph. Maybe one represent EQT, one represent King, one represent Microsoft. But most of the time, as you can imagine, the most interesting relations you can usually find are the medium-sized companies or like startups, actually. Because two big companies, their similarity is, you can say, a bit of contaminated by, too many employees have been moving basically everywhere, So that is not distinguishing or discriminative enough in the downstream applications. So sometimes we have to even do a bit of filtering of those kind of overly dominating node in the end. And if we zoom out even more, and this is only, again, represent just a snapshot, a small part of the entire graph. And in the entire graph that we build in the end, it has 1.17 million companies or nodes, and there are more than 51 million edges in total. And by the way, those 51 million edges represent the synthesized and aggregated edges. So it's a pretty big network. It's a pretty big. Do we have some questions? Oh, okay. Okay. Sorry. So we have that. Sorry. Yeah. So now, now we have that graph. Now, sorry. We need to talk about evaluation. Because, sorry. Thank you. Sorry about my voice. It's a bit, bit strange recently. Yeah, we have the graph, and now, now we have we need to use the graph for some downstream applications. When we are talking about downstream applications, we have to map to the typical use cases usually. And we have been talking about some typical use cases, like market mapping, competitor analysis, and merger acquisition. It's not moving anymore. Sorry. Yes. So we actually managed to create an evaluation data set, evaluation task for each of those use cases, at least to try to address that. For market mapping, we created an evaluation task, which is called similarity prediction, SP. And in this case, as you can see, this data set or evaluation task, it contains pairs of companies. And this illustration, for example, it shows how this task is being done or evaluated in real life. You have some seed company, and then you're supposed to search for similar companies for each of those seed company. And the process goes like you take each seed company and trying to measure the similarity between this company and some candidate company. So it's like a binary classification task. You're trying to predict whether the pair of company is similar or not. This is similarity prediction. Competitor retrieval, which is aiming to solve the use case of competitor analysis. This task is more sort of, we're more caring about the recall actually, because the data for this evaluation task is actually from the real investment documents that we have been working with. So we just go through those documents and take, for each interesting company in the scope of investment business, and take all of the identified, you can say, the true competitors. Usually there are about 3 to 6 competitors for each company in focus. So we took that, and then we asked some algorithms operating on this on this graph that we constructed to identify, to retrieve those companies as much as possible. And in this case, for example, the recall is only 5 out of 7. And finally, M&A, merger and acquisition, we designed an evaluation task, which is basically trying to rank the companies as accurate as possible according to the merger acquisition experts' output. They're also obtained from the investment documents in EQT. When we are evaluating different algorithms that can be run on the graph that we built, there are 3 different categories of methods. The first one is edge only, which basically means that you only use the edge information instead of also using the node information. If you remember the 4 vectors that we built into each node. And the second category of methods are node only, which is basically saying that we only use the 4 vectors for each node, which is basically the textual description. And then the final category that we hope that should work the best is node plus edge. So all of these methods, they are utilizing both the node feature and edge feature, or edge information. And the first column of the results, if you can see, try really hard, it says SP. So it's similarity prediction task. Maybe you cannot see clearly, but we conclude that node plus edge methods works the best. It's it's connecting. And then we also evaluated all of those methods on company retrieval methods, and in there we also observe the node plus edge methods works the best. And on the final task, we can see it's a bit bizarre because not the node plus edge methods works the best, rather the methods using only the relation works the best, much better actually. I'm not sure why, because intuitively you kind of wish that the combination works the best, but actually the relation sometimes works better than the combination. Maybe it's because for that particular use case, the description is more like a noise rather than an information injection in that case. Whereas, well, we're still fixing the screen sharing. I want to just continue. And there is actually a 4th evaluation task that we devised after these 3, which is called link prediction task. Installing updates. Yeah, great. I think that's nice. The problem all along. Yeah, we have all the problems. Yeah. Yes, question. Yeah, okay. I'll get a microphone. Luckily, we are not launching a rocket.
All right, thanks. I was wondering about the similarity prediction. I didn't quite understand because I thought that the similarity was just calculated based on the numbers of the nodes and the edges, but it was that instead engaged in other ways. So
yeah, it is.
Train it.
Yeah, it is. It is learned. Well, if you remember the 3 categories of methods, the combination node plus edge methods We are mostly using graph neural nets, especially the self-supervised ones. And those self-supervised ones, because in this graph, we don't have any label per se, right? So it's basically designing some task to predict and trying to optimize that prediction task. One common prediction task is that you're assuming that some of the link doesn't exist. You mask them out, and then you try to learn those graph node embedding and trying to make those graph node embedding to be able to predict those links when you are calculating their cosine similarity, for example. Yeah, so but the node-only methods, it is just the sake of taking the 4 vectors, if you remember, and calculate the cosine similarity, as simple as that. Yeah. For the edge-only methods, it is mostly heuristic-based methods. Basically, we are calculating, for example, shortest path, for example, trying to compare between two companies, which one actually has a shorter path to each other. The shorter means that they probably stay closer to each other. So it's very different from category to category, but generally speaking, the combination node plus edge, the green one, are mostly the state-of-the-art graph self-supervised learning methods. Yeah.
Thank you.
Thanks.
So yeah, I was wondering, did you try turning it around? Given a graph, look for a place in the graph where there seems to be little competition and predict the description of the company.
That's an interesting angle. No, we haven't tried. That could be even structured as a self-supervised learning task. Yes. Yeah.
Anyone else? Any questions? Yeah.
So I don't know if these example similarities were from real world, but it seemed that they had quite the time dependency that for you to be able to fit n+1 company into the graph, you need to accumulate a lot of data. And I assume that also has a lot of business implications, that if you're more like private equity or venture capital, you would have like different requirements of maturity.
I'm glad that you mentioned the dynamic aspect of the real world.
It's almost as unplanted.
Yes, it's actually a dynamic graph. If you and the reason why I bring, well, I'm seeing a different slide, but never mind. Yes, it's called temporal graph. So when we conclude this project and submit this project as a paper, research paper for review, we actually automatically get review comments about why don't you guys treat it as a temporal graph, a dynamic graph, because this graph is evolving. Yes, now I'm seeing the right slide. And on the bottom, there is an example of the kind of temporal graph that I was talking about. Actually, if you treat the entire word as an incoming event stream system, each change to the word can be modeled as an added to a graph, and that graph is evolving. And that graph could be a very huge one, like all of the events happen to me, could be linked to yours, and then all of us form an entire graph, or it can be an ego graph. In the company case, it's the company ego graph. So I have my graph, which is basically being built when I was born, and you have your graph, and we can. And then there is this Sweden as a country, as a common node. So me and you got connected at some time, based on when that edge being established. But yeah, this is something that I'm working on right now, but at a different company, different place. But it's a very promising research field.
See you next year then.
Yeah. Thank you.
More questions? Or? I can't see it. I can't see the people in the back.
Very interesting, thanks.
Thank you.
What are the implications of, because you used embedding models 2 years ago, but the the LLM revolution and the stronger language models, do they have an implication for your work?
Yeah, definitely. Even before the emergence of ChatGPT, we try to train because I mentioned we started with company descriptions, right? That is very easy easy data that you can leverage. But at that time, I think it must be like more than 3 or 4 years ago. We tried to learn embedding for those company descriptions. But we realized at that time, many of the methods that we can leverage, they need some kind of labels. You need to identify, you need a fairly big data set showing, hey, this text and this text, it's similar, or this text and this text is dissimilar. At that time, we were working on semi-supervised learning methods, trying to learn company embeddings using very little label data. And the purpose of doing that is that we can sort of store those embeddings into a vector database, and then we can quickly search for similar companies already then. But again, I mean, from, is it 2022, the emergence of ChatGPT, then we can, it basically means that we don't have to train our own model. There is a pre-trained model that we actually somehow evaluated. It works also pretty good already. So basically the emergence of the ChatGPT kind of big model, big large language model, made us sort of free from fine-tuning any language model. That's the change. Yeah.
Okay, thanks.
Thank you.
Thank you. This is very interesting. About the 15 relations between the nodes, how did you select them, and did you do any ablation studies on their importance?
So 2 questions. How do we select those 15 relations? And second one is, did we do any ablations? Selection, I don't want to call it a scientific approach. It's very much business driven. Simply because I worked in the Motherbrain team and in EQT for 2-3 years, 2 years. I kind of have some sort of instinction about what might be important. But more importantly, we talk to other teammates, other teams, especially investment professionals, trying to get their idea what might be important. Another important factor is that we have to consider what we can get hold of as a data source, because you have to, when you want to cook a meal, you have to have rice on your hand side, right? So it's a combination of those factors. As of ablations, we definitely did something, but it's not reported in the paper. I think we can probably say we did ablation on the link prediction task. Basically, link prediction task is, I didn't have time to go through that, but we build the graph up until a certain time point in the past, and then we have a few months going forward, and we use the data coming after this cutoff point as the evaluation, putting all of the links that happened after this time as in the evaluation data set, and then we calculate how accurate that you can predict each type of relations, especially when you're trained jointly or you trained only on that particular type of relation. We see actually discrepancy of performance between different edge types. I think the strongest edge type is still coming from the EQT investment professionals, because we had an investment platform that investment professionals can go in, log in, and try to put companies into different baskets, and we use that data to build the graph too. So that kind of data is with the highest quality, and the data about, for example, co-appearance in news, or even co-attendance of conferences, this is kind of noisy. Yeah.
Thank you. Thank you.
Thanks.
All right, maybe we end it here. So thank you very much, Lele. And yeah, a big
Thank you.
applause to Lele. Right, so we'll just take like a 15-minute break or so, maybe quarter to. I should have said at the beginning, but if we need to use the bathroom, right, the bathrooms are to my left and behind this kitchen area there. Yeah, so 15 minutes and then I'll try to figure this out. Yeah, so thank you. What's happened now? Is it like...
I have no idea. It's just freezes.
How's your throat? Is it all right?
I must be affected by this thing. It's virus.
It's like a virus in there or something.
Yeah. I didn't know what happened.
What a nightmare. Man, I went in and canceled all of my like little slide animations. I was like, no. Like, I don't know the thing.
Did we shut it down?
Yeah.